from the wall at a rate of 1.5 meters per second. So x is getting larger. And we're asked at x equals 4 meters, how fast is the slide going down the building? Okay, so that's the problem. So we need some geometry, and it turns out in this case the geometry is just the Pythagorean theorem. So anytime you have a right triangle, if the problem is posed with a right triangle, then you're probably going to use the Pythagorean theorem. If it's something like a volume or an area, then you use the appropriate formula. So in this case, the Pythagorean theorem says x squared plus y squared equals 10 squared. So this squared plus that squared equals that squared. So this is geometry. So what we've done in the past is you take the derivative with respect to time of each part of the expression, and because the variable is time and these are x's and y's, we use implicit differentiation. So you get 2x times dx dt for the first derivative here, the derivative of the first term, not the first derivative of it. And here you get 2y dy dt, and that equals 0. And we can solve, in this case they want what rate does the ladder slide down the building. So that's what we're trying to find, is we're trying to find dy dt. So let's solve for dy dt. So move the dx dt term to the right hand side. You can divide by 2 and then divide by y, and you get dy dt is equal to negative x over y times dx dt. So that's the relationship that relates the rate of change in y to the rate and change of x with respect to time. So now we see if we've got enough information. So we know what x is, and we know what dx dt is. So we know this one and we know that one. In this case, we don't know y, but we can use the same geometric relationship that was used to derive the relationship between the rates. So we can solve for y, because that's the one thing we still need. So we can solve for y from x squared plus y squared equals 100. So y is equal to 100 minus x, y squared is equal to 100 minus x squared, or y is equal to the square root of 100 minus x squared. And I didn't put the plus because you can't have a negative distance, so that doesn't, sometimes you can have plus or minus, like in physics where you have velocities that can be plus or minus, but in this case you can't have negative distances. So we'll stick the number in there. So y is equal to the square root of 100 minus 4 squared. I was just thinking of something. Yep, okay. So 100 minus 16, take the square root, and you'll end up with y equals 9.17 meters. So now we know everything. Now we know y. So we can go back and plug into the expression to solve for dy dt. So we get that dy dt is negative x, which is 4 meters, divided by y, which is 9.17 meters, times dx dt, which is plus 1.5 meters per second. And what do we get? We get negative negative 4 divided by 9.17. Oh, hold on. Negative 4 divided by 9.17 times 1.5. And so dy dt is negative 0.65 meters per second. So, we have negative, which makes sense because y is getting smaller. As the top of the ladder slides down the side of the building, y is getting smaller, therefore dy dt should be negative. And that's what happens with these ladder problems. You have at least one for homework. If I gave you dy dt and it was sliding down the house, dy dt would be negative and dx dt would be positive. So you just got to be very careful about the signs of the information. Don't just look at the problem and say, in this case, it says moving away. It doesn't have the sign. Away turns out to be positive, but if I said it was moving down the side, down, if y was going this way, if I said the ladder was sliding down the building, I would say it's sliding down at 3 meters per second. I wouldn't say it's negative 3 meters per second. So you've got to read the problem and understand whether it's the rate of change is negative or positive so that you can get the right sign for the answer. Okay, so let's look at the next problem on our sheet. So what we have is a man walking away from a light, and we're asked some questions about it. So to understand it, you've got to draw a picture. So let's make a picture. Make sure you draw this on your paper. Oh, you don't have, that's right. How'd it go? All right. And how did you do?
Played second.
Yeah.
Shot at 85. So the kid that shot even more.
Wow. Yeah. Yeah, the one, if you guys haven't played golf before, the frustrating thing about golf is you have good days and you have bad days, and your bad days you can't understand why you can't just play like you always play on good days. But what do they do differently? So then you start over analyzing your swing. And I used to stand out. We used to have a house. I guess this was when I was a junior in high school, and I was on the golf team, and we had a sliding glass door, and I'd stand out on the deck in the cold weather, and I'd be analyzing my swing during the. I don't know if you ever did that. So, I'd be sitting there, and I get my legs, left foot slightly to the right, then you get your club in the right place, and all this kind of stuff. You'd watch yourself. You don't do it inside because that's when you hit the light bulbs. So you have to go outside to do it. Frustrating. That's why I don't play golf anymore, because if you don't play very often, or if you don't have a chance to practice, it is so frustrating. You can do better, but it's much more frustrating than trying to play basketball every once in a while. Okay, so what we have is a light bulb. So here it is on a pole. And then you have a man, which kind of looks like a light bulb, pole with legs. And the light shines like this, and it goes in the shadow. So here's a shadow, like that. So the man is 6 feet tall. Walks away from the light 10 feet above the ground, so the light is 10 feet. If his shadow lengthens at a rate of 2 feet per second, so let's say his shadow, we're going to call that distance y, and we'll call the distance that he is from the lamp x, like that. So if his shadow lengthens at a rate, so that means dy dt is equal to plus 2 feet per second, how fast is he walking? So the question is, what is dx dt? So this, the speed he's walking is going to be, if you measure the distance from the light pole, the light pole is not moving. So if you measure the distance relative to that fixed point, that is his position, and therefore the rate of change of his position is going to be his speed. So now the question is, what geometric relationship would you use? And you might be tempted to say, well, it's a right triangle, so I'm going to use the Pythagorean theorem. That would be wrong. Okay. So what other geometric relationship might you be able to use? Has to do with triangles. Anybody? Okay. So the answer is similar triangles. Okay. So the triangle that involves his shadow length at a point in time is similar to the triangle that involves going all the way back to the lamppost. So what you do is you compare the ratio of the sides of the triangles, the two similar triangles, and they're similar because they're both right triangles, and they both have this same angle, and therefore this angle has to be the same as well. So all the angles are the same. So in this case, the geometric relationship that relates the distances is similar triangles. So what that would say is that 10 divided by 6 is equal to something divided by something. So what do you think that would be? I'll ask somebody specifically. Let's say Maya. So based on the other dimensions, it involves x's and y's. Give you that much. X times y or x plus y?
X plus.
Right. Yep. So it's going to be x plus y over y, because the long side of this triangle, which has this as the height, is going to be the sum of the two, so it's x plus y, and then the length of this triangle, this side of the triangle relative to this height, is y. So that's the result. So we could multiply it out. 10y is equal to 6x 6x, is that right? Times yes, okay. Plus 6y. And then you could simplify. 0 is equal to, if I subtract 10y from both sides, you get 6x minus 4y. So it's a pretty simple relationship. We take the derivative. So now that we've done that, you take the derivative with respect to time of each part. So I'm going to let you do that because it's really easy. So go ahead and figure out what the relationship, and what we're looking for. It says if his shadow lengthens at a rate of 2 feet per second, how fast is he walking? So we're given dy dt, so solve for dx dt. And the question is, do you know? Well, you don't really need to know what x and y are. You just need to know the when you take the derivative of this, because they're just x's and y's, you won't have You don't need to know what X and Y are. You just need to know these two relationships. So let's see what you guys get. And I'm going to get a drink of coffee. So we had a really good group, our brass band group the other night. We had 3 trumpets, 3 trombones, 2 French horns, French hens, and a tuba. That was pretty exciting. As far as brass bands go, it's pretty exciting. So there's your answer, right? So when you take the derivative of this, the derivative of x is 1, but then you multiply it by dx dt, and the derivative of y is 1, but you multiply it by dy dt. And if you solve for dx dt, which is the speed he's moving, I moved this to the other side, made it negative, divided by -6, which simplifies down to -4 over -6 is 2/3. And then I plugged in my given dy dt, which is 2 feet per second, and therefore he's walking at 4/3 feet per second. Okay, so that one's pretty easy. Okay, let's go to the next one. This is kind of the same situation. A floodlight is installed on level ground 10 feet from the Diamond, a vertical wall on Long Peak in Colorado. The ranger, 5 foot tall, walks away from the light towards the wall at a rate of 4 feet per second. How fast is the length of her shadow on the wall changing when she is halfway to the wall? How fast is the length of her shadow changing when she reaches the wall? What can you say about the length of her shadow and its rate of change shortly after the ranger leaves the light? Okay, so try to draw what that is. It's not exactly what we have. I will, so what you'd have is basically, it's kind of the opposite. You'd have a light down here, and the shadow would be up there, right? So as she's moving away from the light, the shadow should get shorter. But it's still going to be a similar triangle kind of problem. So you should be able to, and you'll need to use a little bit of geometry probably to find, it says halfway to the wall, so that's 5 feet. Halfway between 10 feet and 0 feet is 5 feet. So I'll leave that one up there. See what you can pull together in a couple minutes. So let me ask somebody. The question is, what is the geometric? If you use my particular, I mean, you could use x as this distance. The difference would be is that dx dt would be a different sign than if you have x over here, and you'd also have to do a little bit of, but you could still, you don't have to choose x this distance. You could choose x this distance. Y does have to be the vertical axis. So I'm going to ask, let's see here, who do I want to ask? So Christian, you're going to get, what is the in terms of my definition of the distances, what is the geometric relationship that we would use for this? Yeah, well, you do have right triangles, but you'd probably just still use similar triangles. So what you want to do is, compare this length to that length as this length is to that length. So just go ahead and write that out, and then once you get it, let me know what it is, okay? And don't use 5. This is 10. This stays fixed. This 5 feet is at a particular instance, so you're going to want to use x, not 5 feet. So it's just going to be two ratios here. So anyway. So it'd be 10 over 5 equals, which 5 are you using? This height, or his height doesn't change? Yeah, but we have to use x there. So so this would have, if you're using this 10, then this would you'd have to use x there, okay? And then what's on the other side? Or is that right? So you're comparing this length to that length. So this, okay. So what you're going to do is you're going to compare this triangle to this triangle. So you've compared this length, the length of the long side, or this side of the triangle, to this side of the triangle. So now we have to compare this side of this triangle to that side of that triangle. So we just have to, you have to look at the corresponding sides. So the corresponding side to this within the triangle would be that one, and the corresponding side to this, the larger triangle, would be that. So you'd have, for x, we'd have 5, the corresponding length. So it's this side to that side, this side to that side. So you compare that to that, and relative to the larger triangle, then you'd end up with that. Okay, so it's like, let me just draw just a triangle. And so these are both similar triangles because they have the same angle here, and but they're both 90 degrees. So they're similar. So if I just used numbers and I said this is 4 and this is 6, and then this distance would be, let's say, 10. What is the distance here? Question mark. What you do is you'd say, there's two ways you can do it. You can compare within a triangle. So you could say 6 over 4 is equal to question mark over 10. So you're comparing this side to that side and this side to that side. Or you could do it across triangles. So then you compare this side to that. In this case, we're doing it within the triangle. Here you're comparing sides. So you could also do 4, this length of that triangle is to that one, as this side is to that side. And you see you get the same, if you cross multiply, you're going to end up with 4 times question mark is equal to 60, and you get 4 times question mark equals 60. So it's the same relationship. You get the same solution whether you compare the sides of two similar triangles within the triangles or you compare the sides. So that's what we did over here, is we would, let me erase this stuff. So what I did is I compared this length to the length, this side on this big triangle to this side on the smaller triangle, and then I had to compare the long side, this side, the shorter side on the big triangle to the shorter side on the other one. So in the previous example, you remember what we got, where was it here? We had something like that. So we ended up with a nice linear equation. Here it's not quite as nice. You get 50 is equal to xy. So that's the geometric relationship you get for this problem. Still dealing with similar triangles, but because they gave us different information. So now we need to take the derivative of that with respect to time. So you're going to use implicit differentiation, but you're also going to use the product rule here. So remember, the product rule is you take the derivative of this times that plus the derivative of that times that. And then you take the derivative of this as well. And so see what you can come up with for your related rates expression. So I'll give you should be able to do in about a minute if you know what you're doing. So if you have any idea what you're doing. I'll give you the hint, the left-hand side 0. Okay. Derivative of 50 is 0. That was real nice of me, right? So this is the problem we're working on here, this one. Okay, like I said, if you can't do it within a minute, you're probably not going to get it. So what you get is x times dy dt. So you take the first term times the derivative of the second, plus the second term times the derivative of the first. So the derivative of y is just 1, but because it's implicit, you put dy dt. The second part, the derivative of x is 1, but you multiply by dx dt because it's implicit. So now, how fast is the length of her shadow on the wall changing? So what we're looking for is we need to solve for dy dt, because that's what they're asking us. So you'd get negative x is equal to dy dt is equal to y times dx dt, and then you divide by negative x, so you get the dy dt is negative y over x times dx dt. So now you just have to see, do we know everything? Well, we're given the speed, dx dt is plus 4 feet per second. And it's plus because x is getting longer as the person walks towards the wall. X equals 5 feet, and y is equal to, well, you can use this relationship to find y. So y is equal to, so if x equals 5, y, you get x 10, y equals 10. Okay. Because if I plug 5 in here, 50 divided by 5 is 10. So now I've figured everything out. So to find the rate of change, all I have to do is just plug in the numbers in. So dy dt is equal to negative y divided by x times dx dt, which gives you negative 2 feet per second, 8 feet per second. So 10 divided by 5 is 2, so 2 times 4 is 8. And that makes sense because as the person walks towards the wall, the shadow should be getting shorter. At the wall, the shadow will be the person's height. When the person's right next to the light, the shadow is really long. Okay, now just to give your brain a break here, I was going to show you something that has nothing to do with calculus. A little interlude. So that's my happy place. Okay. So the second part is how fast is the length of her shadow changing when she reaches the wall? So you look at the same relationship. So part B, what changes is y is going to be the same height as the person, so it's going to be 5 feet, and x is going to be equal to 10 feet. And they're still going to be walking the same speed. They're going to run right into the wall. So dx dt is going to be equal to 4 feet per second until they actually hit the wall. So all you have to do is now use those new pieces of information to calculate dy dt. So you would get negative 4 divided by 10 times the speed they're traveling, which is 4 feet per second. So what is that going to be? It's going to be negative 1.6 feet per second. So what you see is that as they approach the wall, dy dt gets smaller. The shadow is still getting smaller, but it's getting smaller at a smaller rate. And if you look at the last question, what can you say about the length of her shadow and its rate of change shortly after the ranger leaves the light? Well, what will happen there is, x is small and y is very big, and so it's big. Okay, so that's what you can say is that. I mean, the shadow. If you think about a light on the floor, if they're standing right, the light's here, and they're standing here, theoretically the shadow would be infinitely tall. So it's getting shorter at it's getting shorter at a very quick rate. So initially the shadow moves pretty quickly, but as the person approaches the wall, the shadow is getting shorter but at a much smaller rate. So that's how that one works. Okay, let's go to the next one. A hot air balloon is rising vertically. An observer on the ground, 5,000 feet from the point where the balloon took off, is watching it rise. When the balloon reaches a height of 10,000 feet, its velocity is 10 feet per second. How fast is the angle between the ground and the observer's line of sight, the angle of elevation of the balloon changing at this point, instant? So again, try to draw a diagram which would kind of represent what this problem is doing, okay? And put some dimensions on it. In this case, you're looking at angles. So you actually have to use a trigonometric relationship that involves angles. So think about which trig function involves the appropriate sides of the triangle. So think about that as well. But there's, back to the video, there are, each country has, in Europe at least, I'm sure other places too, you've got countryside that, like I'd love to go to Tuscany and do that, or go to Provence in France, southern France, that'd be nice, or the Alps. So let me ask somebody a question here. So if I use the y as the vertical distance between the ground and the balloon, its elevation, Lexi, what is the velocity in the calculation going to be positive or negative 15 feet per second? Positive because, yeah, it's going up. So if it was if the balloon were sinking, then it would be negative, but in this case, it's positive. So what is equal to 15 feet per second? Still Lexi. So what quantity is equal to 15 feet per second? Yep, dy over dt or dy dt. Okay, so that's the dy dt. And as I said, you can make this into a right triangle, but you're not going to use the Pythagorean theorem, but you're going to use, so here's your right triangle. But because they asked about angle, the angle that they're talking about is this angle. So which trig function, Michaela, which trig function am I going to use based on the two pieces of the two sides that I'm interested in? Which side is this? What's that? Tangent. Yep. So the tangent of theta equals, it's going to be the opposite, which is y divided by 5,000. So the distance, this side doesn't change. This side is changing. So I don't put 10,000 in there. I'll only use 10. I'll only need that if I if somewhere in the problem statement I need it. So now we have to find what we're trying to find is what is d theta dt. What is the rate of change in the angle? Isn't that what it says? How fast is the angle between the ground and the observer's line of sight? So that's the question mark. So if I take the derivative with respect to time of each term, I'll get the derivative of the tangent of theta with respect to time is going to be equal to the derivative with respect to time of y divided by 5,000. So we haven't done this yet. I mean, the variable is theta over here. I'm taking the derivative with respect to time. Does anybody remember what the derivative of the tangent is? Probably not. So the derivative of the tangent is secant squared. So you get secant squared theta, but because you're doing implicit differentiation, you would get d theta dt at the end. So this is the variable. So again, you just treat it like a normal differentiation. Look in your book to find out what the derivative of the tangent is, and then you tack on d theta dt, and over here you'd have 1 over 5,000, which is a constant, times just dy dt. So that's the implicit differentiation. And so the question is, am I given all the information in the problem? So we're trying to figure this out. We just said this was plus something, 15 feet per second. This has units of feet. We didn't show it on there, but it does have units of feet. So the question is, what is the secant squared of theta? Well, that's where you end up using the other length. So remember so if I drew a triangle here, and there's theta, this is 10,000, this is 5,000. Remember, the secant of theta is going to be the 1 over the cosine of theta. Cosine is, so the secant is hypotenuse over adjacent instead of adjacent over hypotenuse. So we'd have to use the Pythagorean theorem to get the hypotenuse. So somewhere, here's my calculator. There it is. So let's calculate we don't have to use trig functions. We just have to find the hypotenuse. So you take 5,000 squared plus 10,000 squared. Take the square root. And so what we get, if you So this is going to be 11,180 feet. Okay, so this squared plus that squared. So let me just, that's equal to the square root of 10,000 squared plus 5,000 squared. So the secant of theta is going to be 5,000 divided by 11,180. So you can solve, basically the last thing you need to do is just solve this for d theta dt. So d theta dt is equal to 1 over 5,000, 1 over the secant squared of theta times dy dt. And so we get 1 over 5,000 times 1 over 5,000 divided by 11,180 quantity squared times 15 feet per second. Remember, this is feet, so we'll end up with inverse seconds, which is radians, ends up being radians per second. So let's see what we get here. So we get 11,180 squared divided by 5,000 cubed times 15. And so I get d theta dt is plus 0.015 radians per second. That's d theta dt. Okay. So again, it's all the same thing. We figure out a geometric relationship. We've used the Pythagorean theorem. We've used the equations for volumes and areas. We've used similar triangles. We've used the definition of the tangent. And so once you get your geometric relationship, then you take the derivative of that with respect to time. You should be given all of the information you need except for one piece, which is the part you're solving for, and you solve for that, and then you make sure you have all the stuff to plug in. Sometimes it takes a little extra step to do that, like here, or we use the Pythagorean theorem, things like that. So I'm going to go ahead and officially assign the homework for this section today. So let me put that up. It's not that many. Actually, there's got to be more than that. So let me open up the spreadsheet. I think I originally only had 3, and then people didn't do very well on the test, so I decided to assign more homework. So let me actually find the spreadsheet that has all that in there. So where are we here? Calculus. Must be under homework. There we go. 173 homework list. Yeah. So here's the number. So it's 5, 15, 20, 28. Somebody zoom that in a little bit. So there's actually 7 problems from this section. So there's those 3 plus those 4. So it's 7. 5, 15, 20, 24, 27, 28, 34. So do those, both of those. So those will be due next Friday. And how many more do we have on this handout? We just have one more. So we'll see how you feel on Monday, if we need some more to go through some more examples or not.